Okay, welcome everyone to today's CDAC webinar. If you're also taking part in the March meeting, thank you for taking a break and joining us for this talk. Before starting, I would like to sadly acknowledge the passing this past Monday of Professor Neil Ashcroft. Neil, as many of you know, is a close colleague of us, a close collaborator and advisor in CDAC, and most importantly, really a pillar of condensed matter physics and science as a whole, and we'll certainly miss him. Today's talk will be given by Professor Yogesh Vohra of the University of Alabama at Birmingham. Yogesh is well known in the high pressure field, having worked on a wide variety of problems and materials, and is but now over 4 decades of very active research on high Z materials, molecular systems, superhard materials, and other materials. He's also been very active in contributing to technical advances, including the development of designer anvil techniques that are used around the world. He also is a longtime collaborator. In fact, our first interaction was in the development of techniques to grow single crystal CVD diamond in the mid to late 1990s, work that led to the large CVD diamonds that are now being used in programs, for example, at Oak Ridge. And we've heard about this in our webinar series. Since that time, Yogesh has continued to develop diamond-based technologies for a wide variety of applications, including in biology and medicine. Yogesh obtained his PhD from Bombay University. He was then a postdoc at Paderborn before moving to Cornell, first as a postdoc and then as a research professor. In 1982, he moved to UAB and rose through the ranks, becoming professor and university scholar in 2001, and then director of the UAB Center for Nanoscale Materials and Biointegration in 2006, among his other titles. From 2003 to 2017, he was also a CDAC partner and trained many students who went off to very successful careers in the NNSA labs. So we're delighted you've been able to join us for this talk, Yogesh. We're looking forward to it.
Thank you, Russ, for your kind introduction. I want to share my perspectives on nanocrystalline and toroidal diamonds, which have come into ultra high pressure material research quite recently. So first I would like to acknowledge just a minute. Let me share the screen again. Okay, first I'd like to acknowledge my collaborators at UAB. We have 3 faculty members. Dr. Cheng-Chien Chen is a theorist, and Dr. Wenli B, a former student of Dr. Jim Schilling, is now an assistant professor at UAB. Then we have 2 staff members, which have contributed a lot to the technical development. We have 6 graduate students in the program. And I would also like to acknowledge long-term support from HPCAT and HPCAT staff in the research which I'll be describing. In addition, of course, none of these innovations are possible through long-term support from NNSA, NSF, a graduate fellowship from NASA and US Department of Education. And I would also like to acknowledge that UAB was an academic partner in CDAC and received graduate student support from CDAC. So these are these 3 graduate students whose research I will be mostly talking about in UAB section. So Chris Perrault, who just finished his assistantship at LANO Caleb, who has been a long-term intern at Sandia, and Seth Ivan, who actually is going to be an intern at HPCAT this summer. So a lot of work which I'll be describing, we will be using actually a very key facility at UAB, which is a diamond microfabrication laboratory. And that involves a maskless lithography system, which had played a key role, which means that you can draw any pattern on a diamond, which you can draw on a computer without having to buy expensive masks. And then we have this sputter deposition facility of metals on diamond and some other things which Russ alluded to about the fabrication of electrical sensors into diamond, magnetic sensors, and then the focus of my today's talk is this growth of nanocrystalline diamond onto a single crystal substrate, and then also the focus ion beam machining of diamonds. So before we get into all the technical development, I want to point out some scientific programmatic motivations for ultra-high pressure material research. The first and foremost is, of course, the phase transformation and thermal equation of states for transition metals, lanthanides, and actinides in the 100 to 500 GPa range, which is very important for a nuclear stockpile stewardship program. And this is a picture of an opposed anvil where you have a second stage nanocrystalline diamond grown onto the single crystal substrate. The second motivation for this is also shear strength measurements, which does not normally receive that much attention, but is a really very important parameter in materials modeling under extreme conditions. And this is typical, the radial X-ray diffraction, which is now being extended to multi-megabar regimes. And then, of course, the novel materials. There is a lot of excitement in the community about synthesis of material exhibiting room temperature superconductivity near 200 GPa. And also there are newer area of material synthesis, for example, the high entropy materials, which can be synthesized now under high pressure, high temperature. So I'm going to give you a kind of an outline of my talk. We are going to talk a bit about the shear strength of diamond, what is possible in DAC, history of ultra high pressure research. I have kind of divided up into less than 1991, where of course we hit the limit of the beveled diamond design. Then nanocrystalline diamond came into the picture around 2012. And very recently we had the toroidal diamond anvils, which came into picture around 2018. And I also like to refer to a nice review by Takahiko Yagi, which appeared last year. Okay, so this is really, I wanted to point this out, some brief description of mechanical properties, also for interest, to graduate students who are starting in this field on what is possible in DAC. We know that a diamond is a cubic crystal, and this is the stress strain tensor for diamond. And we have three elastic constants, which are C11, C12, C44. And if we give those numbers for diamond, they are, of course, the C11 is around 1076, Young's modulus 1141, pretty high. But the number which is the most significant for diamond is the very high value of shear modulus, which is 553 gigapascals. And of course, very low value of Poisson ratio. So why is this significant? And of course, again, for some of the graduate students, why we always polish diamond along 100. So if you look at the cleavage energy for cleaving a diamond is the highest for 100 and is the lowest for 111. So in our design of DAC, one has to pay attention to these crystallographic variations. So another thing which is really important to realize is if we look at a simple experiment, like we take a cylindrical rod and we push it along this one direction, what we call as a uniaxial stress, we know our normal stress, which is sigma naught, and we know the stress at which the material will start yielding or will show plastic deformation. So interesting thing is that for this simple case, the shear stress is maximum at this plane, which is at 45 degrees. And the shear stress is half the uniaxial stress. So what it has got to do with DAC is we can generalize this thing to the DAC case, is that we have the maximum shear stress in DAC is a sigma axial minus sigma radial, which is inserted by the gasket divided by 2. So that is important. And then let's look at a very basic analysis of what is the shear strength of a perfect crystal. So this is actually from solid state physics introductory book. So if you take these planes of atoms, which have spacing is around A, the interplanar spacing is around D, and you plot this shear stress as a function of displacement, what you really find is that the maximum shear stress which a material under the simple assumption can take is approximately G over 2 pi, which is about 6. So in other words, what we know is that for the diamond, the maximum shear stress which it can take is approximately G over 6. But in practice, you find that the material never achieve that number. For example, for aluminum, it is 60,000. And that is related to imperfections and microstructures. So obviously we need perfect diamond without dislocation or defect to achieve our goal of G over 6. So let's answer our first question. What is possible in DAC, right? That was our first question we posed. So if we look at the shear modulus, which is 553, divided by 6, so you have about 92 gigapascal is the ideal diamond shear strength, okay? Or a differential stress, which is twice that. So anytime in a DAC, if the difference in these two would exceed 184, we'll have a fracture. Fortunately, at high pressure, we get some help from the fact that the shear modulus actually increases. There are no direct measurements of shear modulus at these conditions, but there are several DFT calculations, density functional theory, which predicts that the shear modulus for diamond at 500 GPa is around 900. So that gives us differential stress of about 300 GPa and the shear strength of about 150 GPa. So those are the important number to keep in mind. So let me now tell you the story before 1991. So we had the highest pressure there was around 421 GPa, which was obtained on a diamond which was flat of about 20 micron, 8.5 degree bevel out to 350 micron. And this is a pressure distribution in that diamond. So what that experiment told us is that the diamond also at that pressure is not optically inert. In fact, you see these color changes in diamond from light yellow to dark yellow, orange, and eventually red and dark red. So one has to pay attention to these things for performing, any kind of spectroscopic measurement. So this was the situation before 1991. So we were dormant for 2 decades. And there was a very interesting development then from group of Natalie and Leonard Dubrowinsky on creating these diamond microannuals from glassy carbon. So they took these glassy carbons, subjected it to high pressure and high temperatures, and created these nanocrystalline diamond. And what caused the most excitement was that they reported a diffraction spectrum of gold up to 1065 GPa. And this was based on an X-ray pressure standard. I should really emphasize that all these pressure calibration at these extreme pressures are based on internal X-ray pressure standards. So this was based on the gold equation of state by Yoku et al., which was calibrated up to around 500 gigapascals. Another very interesting observation which came from this experiment is that they put a nanocrystalline ball in a DAC, had a rhenium sample on top, measured the pressure of about 220 GPa, and then in the chamber through a ruby, the pressure was around 72 GPa. So this gives us an idea of, remember I was talking about the axial stress versus radial stress. So this is something they actually discuss in their paper as well. With this data, which from the previous slide, you can actually work out, and this was actually discussed in their paper, is that for nanocrystalline diamond, the shear strength is 230 GPa. And differential stress is around 462. So these are pretty high numbers. Remember, our simple calculation on single crystal diamond gave us a value of 150 and 300. So this was kind of a very interesting question, that whether nanocrystalline diamond can have a higher shear strength than the bulk diamond. And in material science, it is well known that the strength goes up as you reduce the grain size. And of course, there are a whole field of material science dealing with nanostructured materials. So this technique gave us some idea that is it possible actually, instead of aligning two microball in a DAC, which can be challenging because of the slippage and very intricate sample loading requirement. So this gave us an idea, can we actually grow these nanocrystalline diamond on a single crystal diamond by chemical vapor deposition? So if you can do that, you can take out the alignment issue out of the equation. So you can basically just focus on growing diamond perfectly at the center. So, this was really a challenge which we could address because of this capability to have features down to about 5 micron and even 1 micron in our clean room facility. And the good thing about this system is that this is really easily scalable for doing multiple anvils. And then after we pattern the diamond, then of course we have to put it in a chemical vapor deposition reactor to grow diamond on the exposed area. So this has really taken a little bit of evolution to get where we are. So, so this is actually a 300 micron kilo diamond, where we now have a tungsten mask with a hole of about 50 micron. And then, in fact, in the beginning, we didn't have confidence that we can actually grow nano. So we started with what we knew works best, is to really grow a microcrystalline second stage on top of a single crystal diamond. So that's what was our first experiment, which was like a proof of concept. So we had this mask, tungsten mask, and the mass you can dissolve later on, and all you're left with is this region. It's a very nice, shows microcrystalline diamond growth features. And what we find very interesting with this kind of geometry was that you could actually indent gaskets with this geometry, which is not possible in some other cases. So, of course, the Raman showed us that it is indeed a diamond. There is a very small hint of some non-diamond carbon present. So this experiment actually worked up to about 172 GPa. And those of you who do a lot of high pressure experimentation, you know that if you are using a 300 micron fillet diamond, the maximum pressure you can get to is around 80. So you can already see that, this nanocrystalline at the microcrystalline stage, because the shaping doubles the pressure range. However, what we find is that the diamond indeed fracture in these experiments. I mean, it doesn't show bulk fracture, but there are cracks. And very interestingly, it's not the nanodiamond which actually fractures, but it is the underlying single crystal diamond. So we thought then that it's probably likely due to the fact that we are creating some stress concentrators because of the microcrystalline nature of the grown anvil. So as you recall, we really never polished the microcrystalline diamond which we had grown. So that led us to actually try growing nano diamond crystals onto nanodiamond stage onto this single crystal diamond substrate. This is really very interesting, remarkable that this thing we can grow in about 2 hours time. And this is an electron micrograph of this nanocrystalline diamond showing that the diamond grain size is about 100 nanometer. So not quite the 4 to 6 nanometer, which is used in the NCD micro balls before, but it was our first attempt to grow nanocrystalline diamond. So this also point out to some interesting, of course, we took this, prepared this in a diamond cell and took it to HPCAT, and this bring up a very challenging question which people in this field are facing. This is at beamline 16 IDB. Your beam size is about 1 by 2.3 micron. So we are, of course, very well collimated in the vertical direction. And the beam size is around 2.3 in the horizontal. But if you take into account the tail, it's about 8 micron. So it turns out that if you do experiments with the NCD, and it's also true for some other ultra high pressure experiment, is that even with these small beams, the pressure gradients are so large that you are seeing simultaneous high pressure 100. This is the osmium is HCP. You are seeing both high pressure and low pressure osmium in the same panel. And similarly for tungsten, for BCC, you are seeing both peaks, which are really the limitation of the current X-ray collimation. Nevertheless, this NCD diamond made up to about 450 gigapascal based on a tungsten sample. And these results are published. But what we really found in this experiment is that this seems to be the upper limit with the 100 nanometer size NCD stages. So this gives us actually impetus to really look for growing 4 to 6 nanometer CVD nanocrystalline second stage. Okay. And here is a very interesting shot of, you remember, if you look at the nanocrystalline diamond, we had kind of a flat surface. So basically, you can actually use focus ion beam machining to actually machine out your nanocrystalline diamond, which you grew on top of single crystal diamond. So this is really courtesy of Zolt at Lawrence Livermore National Laboratory. Okay, so this is a nice segue into situation after 2018. So in 2018, there were actually 2 reports of using toroidal diamond animals. So toroidal is that you are shaping a single crystal diamond using the gallium ion beam in the FIB machine. And there were 2 reports. One was from Agnes Devalier reporting 603 GPa. And again, this is really using the Rhenium equation of state from Angelini from 2014. And therefore, from Lawrence Livermore, 615 GPa based on equation of state by Dubrovinsky. So this led us to fabricate some of the toroidal anvil ourselves. And what attracted to us in this case was that one could actually get high quality diffraction pattern, at least in some cases, without the splitting which you are seeing because of the tremendous pressure gradients. So so here you start off with actually a beveled diamond, like the other 2 papers which I mentioned. And basically you machine a dome. And the basic idea here is that this dome allows you to avoid the cupping of the diamond, which happens at very high pressures. And this dome is about 2 to 3 micron by most researchers. So basically you have 16 micron flat, and then there's a dome here, which gradually goes to 0 to 40. And then you have this flat region here, which helps in containing the sample and prevent the gasket outflow. So this is kind of the basic design, and there are, of course, some variations and how you really prepare samples in these devices. So I'm going to give you some examples of the science which has been done with these toroidal diamonds in my laboratory, and then we'll have discussion on what are the future directions. So here are some of the specific examples, and where really toroidal diamond animals have added to the scientific studies and extending some of the pressure range of the materials which have been studied. This is actually a plot from Malcolm McMahon, very recent, which showed the pressure versus these lanthanide elements and what structure we know of. And you will see that for the past several decades, actually, the high pressure what one can get with these rare earth metals have been limited to 200 GPa. And one of the prime reasons is that by the time you get to these pressures, these materials are very soft, and that has led to difficulty in actually obtaining very, very high pressures. So one of the suggestions which came out of this paper was this very, so if I just back off here, we have this monoclinic phase, which is called the MC4. In fact, Malcolm proposed that this MC4 actually can be better described. The diffraction pattern fits better for an orthorhombic 16 atom structure, which is shown here. And what is beautiful about this suggestion is that this really brings lanthanide and actinide system together, because this family of structures are known in plutonium at ambient pressure. It's also known in americium, which are the trans-plutonium elements under high pressure. So this layered structure actually ties down the high pressure behavior of rare earths and actinides very nicely. So we decided to actually look for this phase in detail in rare earths metal holmium. So this is the X-ray data which we obtained. And you can see, we see this entire rare earths sequence plus this OF16 phase. So by the way, copper here is used as a pressure marker in this case. So, so we see this entire sequence of these rare earth structures, including OF16. So why this is important is that now we can actually tie up all the crystal structures which we see in a very simple plot of axial ratio for hexagonal close packed, alpha samarium, double hexagonal close packed, HR24 and OF16. All you have to do is you have to scale the C over A by the appropriate amount, and you can see that the layering of the close packed structure is maintained up to very, very high pressure. So I think this is an interesting development, only made possible because we were able to extend the high pressure range of rare earth materials to 282 gigapascals. So this is the equation of state of holmium measured using toroidal anvils. And here we actually, by fitting our equation of state, we predict a volume change of around 2.9%. And notice the compression here. So holmium is compressed to about 1/3 of the volume at ambient pressure. Okay. So I'm going to move on to now the next one. And the curious question is that what happens to these domes at high pressures? So this is an experiment which we did actually in collaboration with Los Alamos lab, jointly published. This is the tantalum rhenium experiment. So we are using the equation of state of rhenium by Angelini. And this is an X-ray transmission graph. What you see is that the 16 micron thing is more or less flattened out by the time you get to these pressures. And what you dark right here, you see is basically the absorbing rhenium and tantalum sample. But interesting enough, in this case, the quality of diffraction pattern is really very good. So you can actually refine these crystal structures and get a really solid equation of state. So this is the equation of state, work of my grad student, Kayla Burrage, of tantalum. And I want to point out a few things here is that, so the solid curve here is the equation of state of tantalum, which is measured using Angelini equation of state. But if you use the Dubrovinsky equation of state for rhenium, you see that the pressure kind of diverges more than 120, 130 GPa at 300. So I think that really, and then the dotted line here is, of course, a really old shock data. So I think we probably had better data recently. So, so you can see that in the case of providing reliable equation of state, one has to really depend on the equation of state of pressure markers which have been validated. We also have an interest in super hard materials, as Russ pointed out in the intro. We are looking at transition metal borides, and they are a very unique material in the sense that they combine the high electron density of transition metals, which is particularly the case near the middle of the transition metal series, like rhenium or osmium, and combines it with the covalent bonding of boron. So, and these materials actually remarkably show anisotropic compression. And this is actually manifested by this experimental plot of the axial ratio C/A as a function of pressure up to about a pressure of about 360 gigapascals. And this was kind of an interesting observation, and this is actually a density functional theory calculation by my colleague, Dr. Qingqian Chen, and which really explained the reason behind that why C-axis is more incompressible is because of the overlap between the boron and the rhenium charge density along the C-axis. As you can see at high pressures, that charge density actually extends along this. That's the electron repulsion along the C-axis really makes the C-axis less compressible compared to A-axis. So, and this is the highest pressure with the toroidal anvil to about 358 GPa, and this is the equation of state of osmium 2 boron 3. And this you see something very interesting here is that the equation of state does not behave very well in the low pressure region below 50-60 GPa. And that is because these materials have high strength, and the deformation in the beginning, one has to account for the fact that these materials have high shear strength. But of course, when the pressure becomes very large compared to the shear strength, of course, the errors will go down. But nevertheless, it points out to some interesting arguments to really do radial X-ray diffraction for materials where you think that the strength has an important effect on measuring the equation of state of the material. So this is something we have recently carried out. So rhenium diboride is also a ultra hard transition metal boride. So where we have done radial X-ray diffraction, and this is the X-ray radiograph of the sample at 10 GPa, and this is at 74 gigapascals, where now we plot the interplanar spacing as a function of 1 minus 3 cosine square chi, where chi is the angle between the diffraction plane normal and the compression axis. And when this 1 minus 3 cosine square chi is 0, that corresponds to the hydrostatic strain condition. So one can get, for even these ultra hard materials, a hydrostatic equation of state by performing these radial X-ray diffraction. And that's what we have done here. So we have obtained a hydrostatic equation of state for rhenium diboride up to about 74 GPa. Recently, we extended this work to about 170, which data being currently analyzed. But what we really learned from the science from this experiment is that this anisotropy in compression is continue to be observed under hydrostatic compression. So it's nothing to do with the non-hydrostatic stresses in the DAC, as offhand one would suspect, but it is really related to the electronic structure of these materials at high pressure. Okay, so I want to conclude, give you some of my observations and some of the future directions. It is clear that the pressure of approximately 600 GPa have been generated on hard metals using toroidal diamond anodes. Focus and machining, and I think one very important thing is micron level sample assembly. One has to really see how you really deposit sample onto those sample cavities will play an important role in future development of this technique. So as you can see from some of the data with NCD and mills, that there is an unmet need for well-characterized sub-micron beam at national synchrotron sources for X-ray diffraction. There was, of course, a recent HPCAD workshop for APSU, and those needs, I think, will be addressed in APSU upgrade and at other facilities. And I think the upper limit of nanocrystalline diamond needs to be really explored further. There are indications that, as we discussed in the introductory part of my talk, was that the shear strength of the nanocrystalline diamond appears to be higher than the single crystal diamond. So I think further controlled experiments are needed with the 4 to 6 nanometer CVD diamond. At least from my lab point of view, we are looking at growth of 4 to 6 nanometer NCD diamond. And from the case of rhenium, I think from the tantalum equation of state, which I presented, is that the X-ray pressure standard need to be validated by cross comparison with dynamic compression experiments. I think rhenium equation of state by Anzolini has been cross compared. Of course, it is still an extrapolation, but it's, I think, validated by cross comparison. Similarly, I think the platinum and gold equation of state by Yoku have also been validated up to 500 GPa. I think my last part of my talk, I tried to point out to you that even though material strength data might affect the equation of state measurements, but by radial X-ray diffraction, one can generate hydrostatic equation of state, which can be used in pressure calibration. Thank you for your attention, and I'll be happy to address any questions.
Thank you, Yogesh. Great presentation and beautiful work. It was great to see the history of the push to maximum static pressures. Thank you again. So, questions or comments for Yogesh? Just unmute yourself or put them in the chat box. Maybe I'll start by saying I was a little surprised at the beginning that you didn't talk about toughness versus strength, because it would seem that your polycrystalline material is actually tough, and you can actually build in toughness by rapid CVD diamond growth where you want the dislocations present. You want a material that has high strength and high toughness, which has always been a big challenge in material science. And some of these CVD diamond that we can make by high growth rate methods actually have pretty high strength, but most importantly, high toughness.
Yeah.
Diffraction.
Yeah, and I think that's a good point. I think there are, of course, the toughness measurements, the fracture toughness is important. And that's particularly so for, in case of impact applications. You definitely want to avoid brittle fracture. And as you mentioned, the CVD diamond growth, you can avoid the brittle fracture by those built-in microstructures. Yeah.
Okay, Urshan has a question.
Thank you, Ross. Thank you, Yogesh. This was really an excellent overview. My question is with respect to one of the very early slides you have shown, where you talked about the shear strength being at 45 degree being maximum. Do you remember that slide?
Yeah. Yeah.
Yeah. The question is, when this nano diamond fails, does it also fail at 45 degree shear?
No, I think with the nanocrystalline diamond, the mechanism actually is not dislocations moving through the individual grain, but it is more to do with the grain boundary sliding.
I see.
So it's a different mechanism. I think it's that's an important point. I mean, it's I think those 45 degrees. I think when we are building DAC, of course, we have to pay attention that the maximum shear stress is not on the 111 plane, where the cleavage energy is the lowest. But I think for the nano diamond, I think it's an entirely different failure mechanism. It's more to do with the grain boundary sliding.
Right. Thank you.
Okay, Daniel Haskell.
Very nice talk, Yogesh. A question about the nano crystalline diamond. After the growth, do you polish the sort of speculate of the NCD in your electron micrographs? It seems that the culate of the NCD is sort of rough and maybe with steps and such. Is it possible to polish it?
Yeah, no, I think you can polish it, but I think the whole point of microcrystalline growth is that you should be see, that's the thing why we want to go to 4 to 6 nanometer, is that you can reduce the RMS roughness from about for this film, the RMS roughness is about 60 to 70 nanometers. But if you are able to reduce the grain size to 4 to 6 nanometer, then the RMS roughness also goes down. So you can use it as is.
I see. I think you have a previous slide, maybe before this one, where you have another.
That's
micrograph. It's at this one. So that it is a lot of steps on that surface.
Yeah. That's a good point. That's why I think we didn't pursue this further. Is that it would require polishing. Yeah, but it can be polished. Yeah, that's possible. Yeah, it can be polished. But microcrystalline polishing usually take much longer than the single crystal, but it can be polished.
Thank you.
Well, Russ, I have question.
Yeah, go ahead, Larry.
Hi, Yogesh. Enjoy your talk, really. And I have a question. How you explain why toroidal groove allows to increase maximum pressure?
Yeah, I think that's a question. So remember that in a beveled diamond, if you have a culate like 20 micron, by the time you get to around 250, the diamond is cupped. So it is bent inwards. So the basic idea is to compensate for that cupping by making a dome in the center. So that's the basic idea, along with some flattening on the side. Whether that dome can routinely get to 600 for all materials, I think it remains to be seen. The problem is that if you make that dome too big, too high, then it never really straightens up, and you get too much of a gradient in the beginning. So there is really further work needs to be done to really understand the deformation mechanism. But the summary idea is, Valerie, is really counteracting the elastic deformation in the center.
Okay. Well, I thought that one of point of this groove is that it allows to increase contact friction. Because without groove, you have sliding between sample or gasket and diamond. And friction stress is lower than yield strength and shear. And groove, and the same was for cemented carbide anvils for diamond synthesis. So grooves allows to significantly increase friction because then sliding occurs within of material.
Yeah, no, I think it's a combination of both factors, and that's why, you know, there is a flat region. Remember, originally we started with a bevel angle, and then we actually put a flat on the outside. Yeah. No, I agree. I think it's a combination of both the slippage and the elastic deformation in the center.
Yeah, and second, also what we found by modeling that this part of groove which is close to the center, it produces very large gradient in thickness. And the gradient is in inverse proportion to thickness. So actually in this small region, you can get very high pressure gradient, which increases pressure in a flat part.
Yeah. Yeah.
So that is what follows from simulations, and actually this follows also from some pressure distributions, in particular the short and also in other.
Yeah, I think another thing which different groups have tried is also changing the central flat from 16 to 8. So I think there is still optimization which needs to be done with this design.
Yeah, and one more comment concerning diamond. You use just when you analyze maximum strength, you mostly use linear approximation. So it's first order or second order elastic constants. And in reality now from first principle simulation, we know not good, but up to fourth order elastic constants, which includes pressure dependence. And actually, it's possible to analyze with finite element, and we did this actually in more detail, stress strain state of anvil and sample and gasket also, and also some equivalent stresses.
Yeah,
it's not just shear stress, but it's a combination of all 6 components of stresses which produce some equivalent stress for lattice instability, and it's also not necessarily shear instability. So
so my actually thought was just to have a very simple model.
Yeah, I understand.
Using the shear model. Yeah, because I think the reason I wanted to point out was that if you take the density functional theory estimate for the shear modulus, the maximum shear strength for diamond at 500 GPa is around 150. But when you look at the experimental data, you see that that number is a lot higher. So that remains to be seen whether that is indeed the case for NCD anvils.
Yeah.
Okay, Reini Bowler has a question.
Yeah, Yogesh, great to see you in such great shape. Very nice talk. I don't know if I missed it, or maybe you mentioned it, is the term yield strength. You know, many years ago, we did some work and others before that showed that at relatively low pressure, diamond starts to plastically deform. And you mentioned deformation. So the question is, do you ever look at your anvils at that level of accuracy after the experiment?
Yeah, I think, of course, if they survive, Reini, we look at them. Yeah. So, for example, the experiment I showed in the microcrystalline diamond growth, what we really found was that the failure was not in the materials what we have grown, but is underneath within the single crystal diamond. And that is not surprising because shear strength is maximum at depending on the culet of the diamond at some point deep inside the diamond. So, but in terms of doing proflometry, we I mean, from the optical fringes, what we can see on the diamonds, which have survived, we do not see, like I would say, within sodium lamp 500 nanometer. I would say within 50 nanometer deformation. We don't see anything at that level.
Well, one of the first examples of that was the classic work by Mao and Bell in the late 70s using SEM. And you could actually see flow of diamond on the surface by SEM. And I don't know if people have gone back to that relatively simple method to look for plastic deformation.
I mean, we have a paper on yield strength of diamond when I did this with Mikhail Ermitz, and it's rather low. And I don't know, is it wrong then?
What was your number, Rainy?
I think it's 1.3 megabar.
130. Okay, so that is that would be put it like 65 GPa shear strength. Yeah, that's yeah. It's versus simple model is 90 GPa. So yeah.
Maybe if somebody else, I have another comment which I have made previously. You call things pressure markers, and that implies that it's something known. But actually, a pressure marker is measured against another pressure marker, which is also unknown. So we're all comparing unknowns. And
that's a good argument. I think it all eventually boils down to shock determination of equation of state. So
I think we should put a lot of effort, more effort in theory of reducing shock data, like in the thermal corrections, because I think the old gas gun shock data are probably very accurate in both pressure and volume. It's just
yeah. But Rainy, the sum of all the equation of states what we are using, Anzolini and Yoko, they have all been validated with the shock equation of state. Yeah. No, I agree. I think it's the shock equation of state, the isotherm, which is really the primary calibrations.
But if you have an independent measurement of the bulk modulus or acoustic velocities, and you have a measure of the volume, then it's independent. The trouble is those measurements haven't been done above, say, 0.5 megabar.
Yeah, that's a good point, Russ. I think the so-called absolute equation of state, I think, is still elusive in the pressures we are talking about.
Right. More questions? If not, thanks very much. We had a great turnout, over 60 participants. Great talk, Yogesh.
Yeah, thank you, Russ, for the invite.
Thank you, Russ.
Thank you.